the Colloquium. So welcome everyone, and thank you for coming to Colloquium. And let's start with the land acknowledge. I think we should acknowledge that Queens is situated on traditional Anishinaabe and Haudenosaunee territory, and we are definitely. I am grateful to be able to live, learn, and play in this land. And I'm, as a new immigrant in this country, invited by uninvited immigrant, I'm still trying to figure out where my position is. But at the same time, one thing that is clear to me is that I need to learn and support the indigenous people's life and the culture. And I'm trying to do my best whenever I have the time. And today, just because we have a beautiful snow that Amy is going to be envious of from California. So I was looking at what indigenous people are doing during the winter time. And I learned that they are moving from place to place during the summer and fall and collect the food. And the winter is really good time for them to talk about the stories. And as you can imagine, all these stories are sort of aiming toward the children. So there's a lot of stories that I think my child will like why the fawn has spots and why the porcupine has quills, things like that. So I'm definitely going to search for it. But one story that I just quickly read and really wanted to recommend to people to read is something called the Nana Buzu. And first, the Niwebibun Miwewin. I totally butchered the pronunciation there, but that's about winter giveaway. And I thought that that was beautiful stories. I recommend you to read. It's also pretty short. So with that, I will introduce our speaker today, Amy Furniss. So she's my colleague in VERITAS, and we've been knowing each other for more than 10 years now. So she graduated Humboldt State University and got the master and PhD from UC Santa Cruz, and did the postdoc at Stanford University. And currently she is an associate faculty at California State University, East Bay. And so again, I'm pretty sure Amy is very envious of our really thick snow that we have on the ground right now and all the shoveling. So Amy is currently deputy spokesperson for VERITAS High Energy Gamma-ray Observatory that I am also part of. And she is also having always really active on outreaching and the equity and diversity, and has been leading the effort inside the VERITAS to improve the equity and the diversity inside the VERITAS as well as overall communities. So if you are interested in talking either about high energy gamma ray or diversity, please stay after the colloquium and talk to Amy. And today she is going to talk about adventure of energetic photons. And I think this is at least my first time attending this active way of colloquiums. I'm really looking forward to hear what she has to share with us. And with that, I will lead the Amy to lead the colloquium.
All right, thank you so much, Nahi. Yeah, so I am going to try to get us to interact with this, but at the same time, I'm also going to trick you into learning a bit of physics. This is something that I have created and done successfully a few times now, in that, I don't know, maybe you guys can use your raise hand function or a thumbs up function, but who here is over Zoom meetings? I'm over Zoom meetings, I can tell you that for sure. It's very hard to engage. It's very easy to get distracted by the other things on your screen. So this is an attempt to have it so you can interact with the material. And what we're going to do is we're going to follow this energetic photon in what I refer to as a choose your own adventure kind of story, where you get to make the decision of what happens to the photon, which in the perspective of particle astrophysics is actually, we're kind of playing with the probability of how this photon is going to interact with its environment and what is going to happen with that. And we're going to try to study the photon from here on Earth. To give you an idea, I did get a quick introduction, so I won't repeat my introduction, but this is VERITAS, the telescope that both Nahi and I work on, and we're building the next generation of telescope, which is also at the same site down in Arizona. And I'm not going to talk too much about VERITAS itself, but it is kind of the end game. We want that photon, that gamma ray photon, to make it all the way to Earth. This is who I am, and it's professionally who I am, but it's a very small slice of how I represent myself. So as mentioned, I live in Santa Cruz, and you guys get to shovel snow, but I get to go play in the ocean year round. So I guess it's a sacrifice I'm willing to make. I'm mother of 2 boys, and I like to say that it's the best work of my entire life, also the most challenging. As a physics faculty at East Bay, I am dedicated to improving access to underserved populations within physics and STEM in general. And I was doing that before we were forced online. I was doing that by using kind of technology and remote access. And it seems to now be perfect timing to have it be something that's more standard, since we all now understand how the Zoomiverse works so well. As I'm going through this kind of talk, I would like you to feel comfortable to what it always feels like is rude, but interrupt me. Verbally, you can unmute yourself and ask a question. You can raise your hand, and I will try to follow raised hands in the chat, except I will very likely be distracted. So if you've noticed somebody's asked a question and I haven't, feel free to stop me. All right. So the way that I've set this up is there's actually a way you can make active buttons inside PowerPoint, and those active buttons will lead to different slides. So we're not going through this Photon's life serially. We're going to go through this Photon's life depending on how we want this, what path this photon is going to follow, whether they're going to interact with a photon locally, or whether or not they're going to interact with a photon on their extragalactic journey to us. So we'll use those active buttons, but you guys get to decide which path the photon travels, and oftentimes the photon will be destroyed. So that our goal is, in the end, with science, what we want to do is we want to be able to study this photon, and in order to do that, we need the photon to make it all the way to Earth, and it needs to interact with one of our instruments that can detect the energy of photon that it is. All right, so we are going to use that's what this text is all just what I said, but we are going to use the polling inside of Zoom. So every time that there is an option to make a choice of where this photon is going to go, I'm going to release a poll, and you guys are going to vote, and we're going to go with the majority. There is, however, a probably 15-minute long introduction to how this photon was born. And it kind of parallels the superhero's origin story. So first, just getting to know our little photon. It's a gamma ray photon, and here you see the full spectrum of electromagnetic energy. You can go down in energy for radio waves. You can go up from the visible light to gamma rays, and there's examples of all these kind of terrestrial, excuse me, these terrestrial things that emit light that is at these energies and at these wavelengths. Well, the energy of the photons that I study and that I'm talking about in this particular instant are actually over to the right-hand side of this slide. So off the scale of anything that's actually produced here terrestrially on the ground. And so the energies are only accessible in the physics processes that are happening. They're only accessible by studying astrophysical objects, such as those in our own galaxy, which is that's Nahi's kind of expertise, but also outside of our own galaxy. And since they're born outside of our own galaxy, we can use them in order to understand the environment that they have to pass through in order to get here. Excuse me. Okay. So extreme origins. Where did our gamma ray photon come from? It's a cute little gamma ray photon. I don't know why I personified this gamma ray photon, but why not? Because we're scientists and we can do whatever we want. They come from a galaxy, but it's not just any galaxy, and it's not just from anywhere within this type of galaxy. So the type of galaxy that we're talking about that produces gamma ray photons, and the type that I study, are blazars. So these are a subtype of quasar, active galaxy. So the galaxies that have an accretion disk and a supermassive black hole at the center, and then jets that are actually emerging kind of perpendicular, almost perpendicular to that plane of the accretion disk. And that's just a quasar or active galaxy in general. The blazars that we study are a geometrically selected subset. So the jet is pointed directly toward us, the observers. And so we see kind of beamed emission And it's like looking down the barrel of a gun or looking directly at a flashlight. So things look a little bit differently, even though the processes we would expect that are happening inside these sources to be the same, whether the quasar is pointed with the jet at us or not, but we can study them best when the jet is pointed at us because we can see things the most clearly, or the photons the most clearly. So that's where our gamma ray photon was born. These objects, blazars, they're some of the most energetic objects within the universe. They create photons up far beyond 10 TeV up to 100 TeV. The problem is getting those photons across the extragalactic distance to us. As I said, they're the geometrically selected subset, and we have been able to actually take pictures of the possible location that these gamma rays are coming from. One of the challenges is that when we're looking directly down the jet, it just looks like a point source. The beaming effect kind of makes it so we can't quite determine the location of the gamma ray itself. So we don't know whether or not our little baby photon was born very close to in the vicinity of the black hole, or perhaps, so you have here the picture, the first picture, it's the first Facebook profile or Spacebook profile of a radio galaxy, and you can see the accretion disk and the black hole. We don't know if the gamma rays that we're looking at are coming from that vicinity or if they're coming from farther down the jet. So you're actually looking at this same source right here, but now way zoomed out so you can actually see the jet, which is slightly off from being pointed directly at us. And we're looking at it in different kind of energy ranges. So you have X-ray, you have radio, you have optical, and you can see some structure in the jet in all of these different wavelengths. And so we want to know how the photon is made. These are the questions that we're asking. How is this gamma ray photon made, and where is it made, and what kind of implications does that have for the kind of physics that's going on in these kind of extreme sources? Okay. So this, we have an idea of how they're made, not necessarily where they're made, but how they're made is in a very special relativistic way. We have a blob of photons. And if you go back, so let me explain, this is a very complicated simulation that I created with PowerPoint. Well, it doesn't simulate anything, it's a static picture. So you have an accretion disk down here, and then you have a blob of electrons and positrons that is moving down the jet. So here's your accretion disk, your supermassive black hole. You can see the mouse, right? Can people see the mouse?
Yeah, we can.
Okay, so the supermassive black hole would be around here, and then the blob of electrons and positrons would be moving perpendicularly away from that. And we have evidence, observational evidence, that this is what we're looking at. So if we back, these are the blobs, the potential blobs that we're talking about right here. You can see these regions that seem like something is happening. And when you have these blobs of relativistic particles, not only do you have these particles moving around inside the blob that close to the speed of light. So each one of these little particles is moving close to the speed of light, 0.9, 0.99 c, but this entire bulk of the blob is moving down the jet at close to the speed of light. So zooming way out, you can see all of these images are cartoon renditions of what we expect to be happening inside of these things. You have your accretion disk, the black hole at the center, magnetic field lines that are spun up because they're embedded within the black hole, and the black hole is continuing to speed up. So you have magnetic field line structure down the jet, and you have these blobs. So this blob would be located right here. All right, so we still haven't talked about how this structure would create a photon. But if you go back to your first electricity and magnetism class that you ever took, you learned that if a charge is accelerated, it will emit photons. So if you have a magnetic field, the magnetic field is going to cause a charge due to the right-hand rule. Well, right-hand rule if it's a positive charge, left-hand rule if it's a negative charge. But because it's a charge, there's a force on it, and it causes it to follow a helical path. And so it is accelerating, centripetal acceleration, again, physics 101, it's accelerating, and therefore it's going to emit photons. The stronger the magnetic field, or the faster the moving the particle, the higher the energy that it is going to be emitting these photons. So this is the same kind of process that's actually happening that within our atmosphere with the magnetic field of the Earth and the charged particles that the sun spits at us. So we see these beautiful kind of phenomena, but it's like blue and green light. So the energy of this kind of phenomenon here on Earth, with our magnetic field being relatively low and the charged particles not moving necessarily relativistically, emits photons that happen to be in our visible spectrum. And this same thing happens if you have a charged particle and another magnetic field, and the energy of that photon is dependent on magnetic field strength and the speed of that said photon. So here we have our particles, they're moving around. There is a tangled magnetic field inside of this blob. Just think about this blob as a spherical cow, because in physics, like, we can make the problem as complicated as we want, but we don't have the ability to measure anything to anything less than just saying that it's a blob. So you have a blob of these charged particles, a magnetic field, and they create photons. The magnetic field and the electrons and positrons, they are energetic enough and the magnetic field is strong enough that they create X-rays. So an X-ray is a lower energy. So if you come back down here, an X-ray is still higher energy than a visible photon, but it's not as high as a gamma-ray photon. So we still haven't created the gamma-ray photon, which is the main focus, the main character in our origin story. But if you have a whole bunch of X-rays that are floating around now, they've been created within this blob from these charged particles going in circles around magnetic field lines, you can actually create a gamma-ray photon from an X-ray photon. And how that happens is now jumping into your first modern physics class where you learned about Compton scattering. Compton scattering, let me remind you, you have a photon come in and that photon bumps into a charged particle, and the charged particle steals some of that photon's energy. So you maybe have a blue light photon come in and a red light photon move out as they've interacted, as this electron has stolen some of the energy. While this wouldn't help us make an X-ray photon more high energy, it would actually make that X-ray photon lower energy. And don't get me wrong, some of this is happening, except we're at such high energies that the process that is actually occurring most often is inverse Compton scattering, where the photons are stealing energy from the electrons and the positrons. So that's called inverse Compton scattering. And this is how our little main character gamma-ray photon is born. So we have an X-ray photon come in, and you have relativistic electrons or positrons, and that relativistic electron or positron gives its energy away to make this X-ray photon a gamma ray. So this is inverse Compton, and upscattering is what we call it, because it scatters at up to higher energies. And that's how our little blazar, or our little gamma ray photon inside of a blazar is born. Now we have our first kind of junction or decision that we have to make. Now that we have this photon that has been born, what is this photon going to do? What are they going to do? So another cartoon image here that I show of a standard active galaxy, and it's not showing us with the jet pointed directly at us, but the sources that we study, again, those have the jets pointed directly at us. And it's got some kind of anatomy to it that we expect from studying these kind of sources at every different angle and every different wavelength. So you have the black hole, and that's very, very small. And then down around the black hole, you have the accretion disk. There's oftentimes an obscuring torus around these objects, depending on their environment and their age. And then we have these jets that are emerging from the vicinity of the black hole. The jets are not emerging from the black hole. Nothing escapes from a black hole. That's still not been broken. And then we have these little chunks of gas that are floating around. And there's the broad line region and there's the narrow line region. So this photon, if this photon is created, this gamma ray photon is created down here, very close to the vicinity of the black hole, in order for this photon to reach us so that we can do physics with it, this photon is going to have to get out of its environment. But it has a probability of not making it out of the environment necessarily without interacting with its neighborhood. So these are our three options. Our main character, the gamma-ray photon, can hang out with a photon from the same neighborhood. He can go and explore the broadline region, or bust out of the boring old galaxy and start the extragalactic travels. So I'm going to launch the poll, and I'm going to give everybody 1 minute to vote, and then we'll go with the answer that everybody chooses. Okay, we have halfway votes. Good. Ooh. Okay, we're tied. Anybody want to throw one more vote? Anybody? One more vote? All right. So we are tied between exploring the broadline region and busting out of the boring old galaxy. In the interest of education, you guys came here to learn something, right? We're going to explore the broadline region. So here we go, exploring the broadline region. So that's this right here, down here, close to the vicinity of the black hole where we think our gamma ray came from. Another artistic rendition. Now this is just an eye that represents the observer looking down at the interior of a blazar, and you can see again the same anatomy where you have the black hole and the accretion disk, and there's a dense torus. And here you have the broadline region as shown as not just clumpy gas pieces, but kind of an overall little cloud of gas that's close by, and a narrow line region, which is more clumpy gas that's farther away. So why is the broadline region called the broadline region? Well, it's because it creates, drumroll please, broadlines. Yes, we are very creative here in physics, and we've called it what we saw broad lines. So if you have gas particles and they're moving around, they're going to have the spectral signature is going to broaden. So here, a nice cartoon rendition of this is gas particles at rest, and you look at the emission spectrum of these gas particles at rest, and they are, to within quantum mechanics, they are just perfect discrete lines at the relative energies of those transitions for the electrons within the shells. And here, if you have those particles moving around, so now they have some velocity moving around, and because they're moving around, their lines actually broaden out. So why do we have a broad line region and a narrow line region? Well, the reason is because, wait, let me make sure. Oh, the reason is because I have to go back there. When you're moving close to the central mass, you're moving relatively quickly. And so the velocity of that central, of that closer gas is going to cause a broader line than the gas out here, which is not moving as quickly because it's farther from that central mass. And so it's creating narrow lines here and broad lines here. So we're going to interact with this gas that's close to the supermassive black hole at the center. And when a photon interacts with matter, it has a lot of different kind of cross sections, different kind of interactions that it can have. And the probability of these interactions is actually based on the energy of the photon that is interacting. So here you can see the energy of the photon that's interacting and the relative cross section, which means the relative probability that these are going to interact and how they're going to interact. And so here you have depending on what the absorber or that broadline region cloud is actually made of, it does change. But what you'll notice is the higher energy of the photon, the more prominent you have a peak around here, the pair production is actually going to be the dominant interaction. So what's going to happen to our gamma ray when it interacts with the broadline region, very likely is it's going to pair produce. So you have a photon that's coming in, our gamma ray photon's coming in, going to the broadline region, wants to have a drink, hang out with his friends, but he interacts and is destroyed and turns into an electron and a positron pair. So it doesn't make it to us, And that's the end of that story. And then you just have extra electron positron pair there to annihilate within the broadline region. It's very sad, very sad. Haven't been able to do science yet. But don't worry, we're going to go back and we can make it. That's the best part of choose your own adventure physics, is that this, even though this is happening, some photons make it out of the galaxy. So let's go that pathway. Is everybody good? Let me check in. Is everybody following? Thumbs up, thumbs down, tears, laughing? Okay, I got some people interested there. That's good. Good enough. All right. All right. So now unfortunately we killed our photon, but you know, it happens. It's nature. We're going to now allow that photon to escape and bust out of the boring old galaxy. Dun, 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 another artistic representation of what it might look like with this jet and the accretion disk and the dusty torus. Of course, we can't get pictures like this inside these objects, but you know, for Hollywood movie kind of physics, it's fun. So now we have our gamma-ray photon busts out of the galaxy, doesn't interact with any photons or photon fields within or matter within the galaxy, and is making its travel all the way to Earth. Now, this travel to Earth is, it's kind of a long trip. I mean, it's longer. There's not a lot of traffic, but there's a little bit of traffic, but it's a really long trip. And let me give you guys an idea of what I mean by a really long trip. So what we do is we measure these galaxies in distance in terms of what we refer to as redshift. So redshift has to do with a Doppler factor that you are measuring of the photons that are coming from the blazar. And since the blazar is moving away from us, they are redshifted. All of the photons that we get are redshifted compared to what they would be if photons were emitted by an object that is at rest. The most distant object that we have detected gamma rays from is approximately a redshift of 1. Now, it's not common. The closer the object is, the more gamma ray photons we detect, and you'll understand that in a moment. It has nothing to do necessarily with the physics of the object, but more to do with the interaction of that photon as it travels to us. So for a redshift of 1, what that's telling you is that this object is 8 billion light years away. The universe is plus or minus a few a billion years, is about 14 billion years old. So that this 8 billion years away, that this photon light years away is, it takes half the life of the universe for the photon to get to us. So this photon has been traveling for half of the universe's life before it makes it to Earth. And even more incredible, in my opinion, is that it takes so long for the photon to travel, moving at the speed of light, for the photon to travel from the galaxy to us, that the universe has had a chance to significantly expand beyond what it was when the photon was emitted in the first place. So while the photon is traveling, they're losing ground because the universe is expanding, and so they don't have to travel 8 billion light years. In order to get to us, they have to travel 10 billion total light years, because 2 billion light years have been added to the distance in between us and the galaxy while that galaxy is actually moving towards us. That is a very mind-blowing to me. It's very cool to think about how we can study these objects, but we're not studying these objects in the real time. We're studying these objects when we get a photon from a blazar that is at a redshift of 1. That photon is telling us about this blazar as it was 8 billion years ago. So, which is still cool, but if we want to know what this galaxy is doing today, we are out of luck there because of that whole speed limit with light thing. All right. So in this very long travel that we have from the object to us, we can take this travel solo. So we can keep to ourselves, kind of put our heads down and just, you know, drive I-5 or whatever. I have no idea what freeways are out there that are really long and boring. Or you can kind of hang out with, like, find a friend that's a low energy friend, kind of hang out with on your travel from the galaxy to us. So now I'm going to release, this is our next junction. I'm going to launch the poll. Okay, you have 1 minute to make a decision. All right, we got some good votes. There's no way to change it now. We're going to find a cool new friend. I love how social you guys are. We're going to find a cool friend, low energy friend on our way from the galaxy to the Earth. So, all right. So what does that mean? Well, we're going to find a optical photon between us and the galaxy, or between the galaxy and Earth, I should say. And where does this optical photon come from? I mean, they have an origin story as well. And where this photon is coming from is the fact that every single photon that is created in the universe is within interactions, of course, is still present. It doesn't have anywhere to go. It's not going to leak out of the universe. So if you have a star that was born here, you have the universe is born, Big Bang, inflation, randomly acceptable there, some dark ages, and then you have some structure formation that has to do with, how dark matter interacts and how baryonic matter interacts. And then you have this kind of creation of the structure that we see in the universe today. As these structures are created, they're like stars and galaxies, and they're creating light, optical light, lots of optical light, because that's what stars emit a majority of. They emit in all of the bands, but the majority of their light tends to be an optical band. And those photons are absorbed by dust and then re-emitted, and so they're kind of around, or they're just floating around the universe because they don't have anywhere else to go. So we find this cool photon. They're just hanging out, and we're going to interact with them. The photon that we find, it is admittedly a old image for explaining what we refer to as the extragalactic background light, but I think it's the best still to this day representative kind of plot that shows us that we can kind of model what we think the extragalactic background light is. So that's the low energy optical light that's just pervasive throughout the universe. But our measurements are really challenged because we're kind of sitting in a bucket of photons that are local. So our sun creates photons, the stars in our galaxy create photons, our galaxy itself with the interactions of charged particles with our galaxy create photons. So we can't quite decipher what is extragalactic outside of our galaxy and what is galactic. So this right here is the relative intensity, and it's from an astronomer. So astronomers tend to make the wavelength increase, which is the energy decreases to the right. As a particle physicist, it hurts my head to think about it, but this is optical light and this is infrared light. So what you're looking at is this is the relative intensity of these photons out there in the universe. And these photons right here are the photons that are coming from, that are emitted from a star when it's born and lives its life. Then those photons can be absorbed by dust. And when they're absorbed by dust, they're re-emitted at a lower energy. And so this is kind of re-emitted photons from the dust. And these measurements, you can see, don't really agree with what our theories, these theoretical lines are. And that's coming to a close. We're finally kind of decided on, at least in the z = 0, which means the current universe, the non-redshifted universe, we kind of know the density of the extragalactic background light, but how that has evolved as you move it back in redshift space, we are still completely uncertain on that. So we're going to pick up a photon friend that has a wavelength of about 1 micron, so in the optical band. And what happens is we don't interact very nicely with our low energy optical friend. So particle physics is always causing trouble, and you have your gamma ray photon and your low energy optical photon, boom, magical particle physics happens and you pair produce. So both photons are destroyed. The energy is never destroyed, but you create an electron and a positron. That electron and that positron don't actually make it all the way to Earth and are detected. So you can see kind of the cross-section energy here. It happens, the most likely, the largest cross-section, largest probability is when you have a 1 TeV photon. So this is our gamma ray photon, and our 1 EV, kind of an optical light photon when they interact. So that's kind of an infrared light. When these photons have energy that add up to more than twice the mass of the electron, then you can create an electron and a positron pair. But is this actually the end of this photon's path? Well, if you're really strictly thinking about it, not necessarily the end. So this is the interaction that's happening. You have some galaxy that's creating light, and you have a blazar that's creating gamma rays, and they interact and they produce an electron and a positron pair. And we're trying to make this photon, make it all the way to Earth. What's going to happen? Well, the story could be over, or the story doesn't necessarily have to be over. It depends on where this interaction actually happens within the universe. So we're wondering, is the interaction going to be happening somewhere where there is a large magnetic field or a small magnetic field? The magnetic field from this extragalactic object to us, it varies. Not only does it vary, we don't really know how strong or weak it is to within some good limits. But we can make the expectation, or we can apply what we know about magnetic fields and how magnetic fields are created in order to determine whether or not these are going to interact in a high magnetic field zone or a low magnetic field zone. So before I go into which zone this is going to happen in, I'm going to let you guys determine, are we going to have this interaction happen in a part of the universe where there's not really anything there, no magnetic field, so in a void, or are we going to have this interaction occur in a relatively high magnetic field, busy part of the universe? So let me release that poll. So you have to make a decision between these two options. You guys are pretty quick, so once we get a majority, I'll stop the poll. Okay, so I'm going to end because there's location with a large magnetic field and ending the poll. So large magnetic field, which one of that is that? This one's right here. All right, so what do we mean by a large or a high magnetic field? Well, let's kind of list the magnetic fields of objects that we know. If you have a really big object, the magnetic field is going to be relatively low. I mean, it's an energy density argument here. So magnetars, they're relatively small. 10 kilometers or so, and they have a really high magnetic field, like 10 to the 11 Tesla. Earth magnetic field, much, much, much lower, so -4. Milky Way, much larger, much smaller magnetic field. And then you can see, okay, so let's make this size even larger, the extragalactic, and it's 10 to the -18 Tesla, question mark. Measuring this magnetic field is extraordinarily difficult, is an open question with a lot of people, one of which is in this Zoom meeting, have done some really good studies in order to determine how strong the magnetic field actually is in this extragalactic space. So we are going to be in a high magnetic field zone for this interaction. And what happens to our electron and our positron pair? Well, the Lorentz force happens again, and those charged particles are accelerated because of that magnetic field. And so they're deflected off of their original line. So they were going to follow a line directly to Earth if there was no magnetic field, because they're still beamed in that general direction. But with a high magnetic field, they interact with that magnetic field. They're deflected off the line of sight. And so what can happen is, just like inverse Compton scattering that we talked about inside of the galaxy, that can happen anywhere. So this photon, or this electron, for example, can interact with a cosmic microwave background photon, another photon field that is pervasive throughout the universe. And it can steal the electron's energy and upscatter to a GeV, so a slightly lower energy gamma ray photon. But that gamma ray photon isn't going to be directed toward Earth, because the charged particle that came from the original gamma ray photon it's been deflected off of the line of sight. So what that means is that we don't detect it. All right, so going back, so we get to see what happens for a photon that is in a small magnetic field. If the magnetic field is small enough, so the low magnetic field, again, maybe the lowest magnetic field in extragalactic space is 10 to the -21 Tesla, question mark. This might be something that's true where there's very, very low density of baryonic matter, which is moving around to possibly create these seed magnetic fields. And so that's why I have these images here, is those voids, which are the largest objects in the universe, even though they're objects made of nothing, we would expect them to have the lowest magnetic field. So maybe we have the low energy photon and the gamma ray photon interact in a void. What would happen if that occurs? Well, so they interact, right here you have your EBL photons, and they pair produce with our gamma rays to create an electron and a positron, but the electron and positron have no magnetic field to deflect them off of the path, but they can still upscatter that cosmic microwave background photon and therefore create a GeV, so a lower energy, but still gamma ray photon to still be traveling toward Earth. So even though we don't have our original photon, which was a 1 TeV photon traveling to us, we now have a GeV photon or 100 GeV photon that's traveling to Earth. So we're not getting the same photon, but we still have a gamma ray photon from the direction of our galaxy that came with energy that was derived from our original galaxy. So scientists were very clever. Maybe we can do something with that. All right. So as this 100 GeV photon is traveling, it's hopefully going to come into contact with some human-made photon detector. And in this case, that human-made photon detector is the Fermi Gamma Ray Telescope. You may or may not be familiar with this telescope, but it is a space-based telescope that is actually just a particle detector in space. So you have the gamma ray comes in, and when the gamma ray comes into this 1 meter by 1 meter particle detector, the gamma ray goes through conversion foils that create an electron and positron pair. So we force the photon to pair produce, and then we take that information, the calorimetry, so we measure the energy of the photon and the direction on the sky that the photon came from, and we're able to determine where that photon came from, how much energy it has, and the time that it came, all things of which we need in order to do science. So that's this single result here is what really can we do as astronomers, photon astronomers, I should say, is we want to know how much photon energy there was, where in the sky did it come from, which means what object did it come from, and when did it show up? Are there a lot of photons in a short period of time, or are there a few photons over a very long period of time? And so that allows us to figure out how the gamma ray photon was made inside of the galaxy itself, or information about where inside the galaxy it was made. So we're quite, again, clever at doing that kind of thing. Now that was one path. My talk isn't over. What we did is we followed this gamma ray photon, made it to the Hall of Fame, but it didn't make it to the Hall of Fame with VERITAS or CTA. So what we did is we didn't interact with photon field or make it through with the broadline region. Then we kind of interacted with a low energy photon. And when we interact with the low energy photon, what ends up happening is we are detected by the Fermi Gamma Ray Telescope. If we are a photon that doesn't interact with anybody along the entire path, so we're just the super antisocial gamma ray photon that's kind of my soulmate photon. We're just going to go in a straight line, no interactions happening whatsoever until we're detected by VERITAS or the PSCT, the CTA. And I wanted, if everybody is okay with it, I wanted to go over this pathway relatively quickly, what happens when we don't interact with a low energy photon. Thumbs up, thumbs down. No interaction. Oh God, lots of thumbs up. Okay. All right, so we're back here at the junction of what would have happened if we decided to be antisocial. So we're going to keep to ourselves. Keeping to ourselves, we're going to get to Earth as fast as possible, which means at the speed of light, because that's the fastest we can move. And you know, if this was what all of the photons did all the time, man, our jobs would be so easy. Like there would not be anything to study, because these photons would be like, oh, there's a galaxy, it creates this many photons, done. But that's not what really happens. A lot of stuff can happen in between. So here, if we have this very high energy photon going all the way from the galaxy to Earth, there's man-made instruments placed around Earth. VERITAS is one of them. I showed you a picture of that. This is an image of a prototype Schwarzschild-Coude telescope that they're trying to work out as to whether or not it should be in the CTA, the next generation gamma ray, ground-based gamma ray telescope. And what happens when the gamma ray hits our atmosphere is it doesn't make it through our atmosphere. So the truth of this story is that no matter what, your gamma ray is destroyed. In order to detect it, it must be destroyed. When it was detected by the Fermi telescope, it was destroyed inside of the Fermi telescope. In order to detect it with a VERITAS telescope, it must be destroyed in the atmosphere. So what happens is the gamma rays that interact with our atmosphere, because of this same kind of cross-section interaction with matter, the photon pair produces somewhere in the atmosphere, and the electron and the positron travel through our atmosphere faster than the speed of light. And I'm not a whack job. That was a real statement. The electron and the positron that are created from the gamma ray do travel through the atmosphere faster than light travels through the atmosphere. So the rule that everybody says of, okay, well, you can't travel faster than the speed of light, it's not technically true. You just can't travel faster than the speed of light travels in a vacuum. But light slows down when it enters into some medium like air or water. But if a particle has enough energy, it can still travel very, very close to that original speed limit of c. So what happens, the electron, the positron that are created from the gamma ray, they travel through the atmosphere faster than the speed of light, and that creates Cherenkov light. Cherenkov light is very similar to a sonic boom, but in waves of light instead of sound waves. So I have a picture here of Cherenkov light, and it happens to show up as blue light, which miraculously, blue light is easy to reflect off of reflective dishes and measure with photon detectors like photomultiplier tubes. So gamma ray telescopes are actually built with optical telescope components, because we're not detecting the gamma ray itself. We are detecting the blue optical light that results from the interaction of that gamma ray with the atmosphere. So we never directly detect a gamma ray. All right, so now we have the option. I'll release the poll, why not? So we have the gamma ray. The gamma ray has been traveling for 10 billion years. This gamma ray hasn't had any friends for the whole trip. Maybe he's pulled over to get a soda or some coffee, I don't know. But they have been traveling for a really long time, and they're coming straight for the telescopes. They've lined it up perfectly, and there's options. So either the telescope operators are sleeping, shame on them, and then the telescope hardware is broken, or the software that runs the telescope is having trouble, so they can't get the telescope to turn on. If there's clouds in the sky, that's going to ruin our ability to detect the photon. The bright moon, we can't observe with bright moon because these photon pools of blue light are very, very dim. They're very dim, so we have to use extraordinarily sensitive light detectors, the photomultiplier tubes, that if the moon is out, it can hurt our sensitivity to these gamma ray photon showers. Or the telescope is just off. So all of these options, they kill the photon. Here, I'll tell you, oh, photon's dead. So poor thing traveled so far, and there's quite a low possibility of this poor photon actually being detected and being used for science. So that's why we try to keep our telescopes operating as well as we can, by having observers come and work on the telescope hardware, software, and pull long nights in order to keep the telescopes on to detect as many photons as we can. So if the telescope operators are present, the telescopes are on, the moon is gone, the weather is good, the hardware and software are working well, we can detect a photon. And we can do science with this photon with VERITAS. So some of the science that we've done, one of our pseudo recent kind of results that we've had is something that has been made possible, and it's very exciting in the context of photons are no longer the only messenger that we use in order to study the universe. Multi-messenger science, so you had gravitational waves and cosmic rays and photons and neutrinos. You can use all of these messengers in order to study these objects. Gravitational waves, not yet for blazars, but cosmic rays, neutrinos, and photons can be used in order to try to determine what's actually happening inside of these sources. So what I show you is a galaxy, an image on the sky, a reconstructed image of a galaxy on the sky that happened to have neutrino detection coincident with the flaring in the gamma ray band of this blazar. So there is a probability, it's not a sure thing, as nothing in science ever is, but there is a chance that the neutrinos and the gamma ray flare that happened for this blazar happened from the same type of physical process. And if that is the case, it's kind of a signature that you would expect if there were protons or hadrons that were at relativistic energies and interactions happening inside of this galaxy. which is one of the biggest mysteries. Are we only dealing with electrons and positrons inside of the galaxy, or are there actually some hadrons in there? And if there are, maybe these objects really are sources of the ultra high energy cosmic rays that continue to pelt Earth once every century or so. So some of the more nitty gritty kind of results from this, but the bottom line is that now with VERITAS, we can look at the sky with other instruments and we can actually get a real view on what the universe might be doing. So with that, I come back to my end slide of what are we really trying to do with these gamma ray photons that have very complicated possible lifetime as they travel from the object to us. We just want to determine how much energy it had, where in the sky it came from, when it arrived, use that information in the context of other detections that might be happening in the multi-messenger kind of view. And we can use that information in order to determine big questions about these objects, like, well, where is the gamma ray born? How is the gamma ray born? What's the galaxy made of? Why does the galaxy behave like it behaves? And we can take that photon and put it into the Hall of Fame through a peer-reviewed publication. With that, I appreciate your attention, and I'm happy to answer any questions you might have about extragalactic gamma ray travel, or VERITAS, or Fermi, or how cute my children are, you know, whatever you want to ask me about. Whatever you want to ask me about. Thanks for your attention.
Thank you very much, Amy. I will